Now I can welcome everyone to what is this, the spring meeting? Spring Technical Advisory Committee of the Tampa Bay Estuary Program. Um, do we want to jump right into presentations or do we want to go around the room?
I don't think we should go around the room because it takes too long and we have a full agenda. But I will say you will notice that the AV setup is brand spanking new in here. Every single mic is live. So if you're used to saying naughty things, please try to behave. But if you do want to say something, it works best when it's, 5 to 6 inches from your mouth. Don't try to eat the mic. If you say something, don't have the mic here because we can't hear you if you do that. If you do want to mute, I think the three little ellipses on the bottom down, it will mute it, but I don't think there's a way to permanently mute it. So just keep that in mind. If you have question for the speaker or comment, pull the mic down close-ish to your face, and that should be good. As far as I can tell, everyone online can hear us, so I think we should be good. But yeah, I think we'll just, one announcement. We have a new staff member on the TPEP team. I'm gonna let her introduce herself.
Communication coordinator. Been here almost 6 months.
You didn't use the mic, right?
I I apologize. Michelle McEachern, Science Communication Coordinator. I've been with the program for 6 months. Thanks for having me.
Welcome, Michelle. Okay.
Okay, feels so official with these microphones. Our first presentation is by Dr. Luis Liscano Sandoval, talking about cloud-based seagrass monitoring. And I believe this is an online presentation, yeah?
Yes, it is. Luis, I've made you co-host, so you should be able to share your screen.
Okay, let's see.
Yep, we're seeing it.
So you see the presentation now, right?
Yep, we see it. You should
Okay,
be good to go.
so all right. So good morning, everyone. Thanks for having me today. I'm going to talk about some of the work I did during my PhD at USF a few years ago under supervision of Frank Miller-Karger. This work was focused on the remote sensing of coastal ecosystems, especially seagrasses. Uh, I think that many of you are familiar with the World Seagrass Distribution Product by the WCMC. The latest version of this product suggests that there are around 300,000 square kilometers of seagrasses globally. However, this product is not complete because there are many areas that have not been mapped yet, and satellite data have been playing an important role in measuring seagrass extent in many regions because it can be used anywhere around the world to detect seagrasses in optically shallow waters. And it can be used to fill satellite data can be used to fill those spatial gaps in seagrass distribution. And now with around 40 years of satellite and multispectral satellite data available, we don't see many studies doing a temporal seagrass mapping at annual scales. And most of the available studies are just mapping distributions at one time and that's it. But what about the temporal changes in seagrass extent? So Some few studies using monitoring data and satellite mapping suggest that seagrasses have lost between 29 and 44% in their stand in Southeast Asia, Australia, USA, and Europe in the last decades. So if we could do this more often in more regions, we could support monitoring the current monitoring efforts and update seagrass distribution maps. Also, we could detect temporal and spatial changes and help to implement more effective management and conservation strategies. So these were basically some of the motivations that I had and the objectives to do this study. Satellite remote sensing is a great tool to support conservation and management, but there are some challenges and limitations on the use of satellite imagery for mapping ecosystems, such as we have here the different temporal resolutions or periods of observation from each satellite sensor. Also, we have that the multispectral resolution is sometimes not enough to separate the spectral signatures. For example, the coral reef and seagrass signatures observed by, for example, Sentinel-2 sensor, which in this plot represent the yellow and green lines in the here. So they can be easily confused, producing misclassifications. And also we have the pixel size. The pixel size can reduce or increase the accuracy of detection because of more details are provided by higher resolutions. Also, well, especially for the detection of benthic or submerged habitats, we have these limitations as well. So water quality conditions must be good to allow observing the bottom, and also the depth. So shallow depths are required given the bottom reflectance is reduced with depth. So usually below 10 meters depth, the mapping of benthic habitats is very difficult. Also, we have the number for the temporal mapping. The number of images will increase as we increase temporal and spatial coverage. We can end up with hundreds of images, which require storage space and computing resources for processing that amount of data. So this is a common limitation for people that want to replicate this type of studies. And of course, we need training and validation data, which is another common limitation for seagrass mapping. There are not many monitoring programs that are consistent over time, or they simply are not very active in taking data, because we know that this takes a lot of work and also a lot of resources to maintain it. And sometimes you can find data, but the data is not always publicly available. So that's a huge limitation. And this takes us to Tampa Bay. I think that Tampa Bay is the perfect place to try a temporal seagrass mapping study. Tampa is one of the sites with two wonderful seagrass monitoring programs that have been active in the last 36 years, such as the biennial aerial mapping by the Southwest Florida Water Management District and the annual Transat data taken by the Tampa Bay Estuary program. These two monitoring programs provide seagrass tent, cover and composition data in the bay and also in surrounding areas in West Florida, such as Sarasota Bay or Clearwater Harbor. So here with this reference data, we were able to train and validate our classifications. Okay, so what about the satellite data? So in this work, I use public satellite imagery, such as Landsat 5, 7, 8, and Sentinel-2. We can see here, for example, for the Landsat sensors, the Landsat, the group of Landsat sensors together, they provide data from 1984 to the present at 3 meters per pixel, delivering one image every 16 days, right? Uh, for the Landsat 7, the Landsat 7 has only usable data before 2003 because after that year there was an error in the satellite producing gaps in the data. And also we use Sentinel-2, which provides images since 2017 at 10 meter per pixel every 5 days. All of this data is available on Google Earth Engine, which is a great platform that allowed us to process and analyze decades of data in the cloud at no cost and at really high performance. Okay, so with a lot of images available from those different satellite collections, the next step was how to identify or how to detect optimal images for seagrass mapping. So I implemented a method using the NDTI, or the Normalized Difference Turbidity Index, for helping and preselecting images for seagrass mapping. So this index is sensitive to turbidity, but also was sensitive to clouds and sounding, as you can see in these images. So, for example, the images showing high NDTI values, which are those values like closer to 0 in this case, those images were usually not optimal for seagrass mapping. So we took the mean NDTI values along with other data such as cloud percentage and valid pixels per image as an indicator to preselect potential images for seagrass mapping. So after selecting the images for classification, we just follow like typical workflows for seagrass mapping, like including atmospheric corrections, cloud masking, training the classifier, which I'm not going to talk because of the time here. So, okay, so after we did classifications, we did classifications like individually per image. So, for example, for the different years, we collected different images, all of as many as possible, the images that we could identify as good images for seagrass mapping. So we can see here that the classification maps can present, it's normal that they can present some noise. So for correcting that, I developed an algorithm that allowed to increase the confidence of seagrass classification and reduce misclassified pixels. So for example, in here we can see that we have 4 images from 2020. So these images are from different days, and every single image can show the different noise patterns, and these patterns can be cleaned by creating conditions on seagrass pixel frequency across the stack of images, as we can see in the images below. So, for example, the first image below shows mosaic of using those 4 images with no conditions. So we can see that all of the noise and the misclassified pixels remain in the mosaic. And for example, the last image shows a mosaic with the condition to remove pixels that were not present across all 4 images. So this way, we can remove the excess of noise. And okay, so with this, we were all set for getting the results. So in Tampa Bay and with the West Florida coast, we were able to classify 63 images and get 16 years of seagrass 10 data between 1990 and 2021 in these 4 regions, including San Joseph Sound, Clearwater Harbor, Tampa Bay, and Sarasota Bay. In the right plot, we compare the satellite data, which is represented by the orange line, we compare it with the aerial data, which is the blue line, and we found similar patterns and trends over time in both datasets. So, and also we had like very good correlations between the 2 datasets. And also the satellite data, with the satellite data, we estimated a 41% increase in seagrass stand in the 4 regions between 1990 and 2021. And the classifications accuracies were between 74 and 88%. However, the time series of seagrass tent was not complete. Some questions remain, like how to get more images and how to better estimate those interannual variations. So for addressing this, I did seagrass mapping at smaller scales in Tampa Bay. So we used the 6 different segments, Hillsborough Bay, Old Tampa Bay, Middle Tampa Bay, Lower Tampa Bay. We used a segment called Manatee River and Terracea Bay, and also Boca Ciega Bay. So this was really useful because we could use images that were not good for seagrass mapping in some segments, but sometimes the images show great conditions for other segments. So for example, in this image, we can see that this is an image showing the NDTI, this index, right? So for example, we can see that there is a cloud in middle Tampa Bay. So that image, we cannot use that image for seagrass mapping in middle Tampa Bay, but the conditions in lower Tampa Bay look very nice. So this was a way that helped us to get more images individually first in the different segments. And also, additionally, the glinted images that were discarded previously were corrected to visualize the bottom and be used for seagrass mapping. As we can see here, it helped to improve the quality of the image. Okay, so with this, we were able to expand the time series from 1990, 2021 to 1987 to 2023 in Tampa Bay. We can see in the graph, the green dots are indicating the new data added to the time series. There were from 14 to 18 new points of data in the different segments. We can see that there were also common gaps in the time series between 2012 and 2014. This was because of there was like a transition between Landsat 5 and Landsat 8, from which there were no data available. Also, we had other gaps in the 90s. This was because it was very difficult to obtain good images for mapping in those years. Then also about the trends, there were we can see that there were continuous increases in seagrass extent, but Hillsborough Bay, where is Hillsborough? Yeah, Hillsborough Bay And all Tampa Bay, we can see that showed declines in the last few years. But also, it was very interesting to see that these two segments show the higher increase in rates in seagrass tent. In overall, we can say that this was a very good result in which the seagrass stand data um, show increases, and that those increases show a good correlation with the aerial data from Southwest Florida Water Management District. Also, we can see that the overall trends in the time series that they were better visualized. Okay, so after this, we just wanted to go further, and we expanded our series mapping for to the Gulf, including the US and Mexican coast, also the Mexican Caribbean and Cuba, which is a work that was recently submitted for publication. But at this moment, I'm going to show some results from the US Gulf Coast, particularly in the states of Florida, Texas, and Louisiana. So we obtained this distribution map showing seagrass areas in purple. I would say this is one of the most updated maps for the region using satellite images from 2019 and 2021. We found that the total seagrass extent was more than 7,600 square kilometers, which is approximately or represent approximately 65% of the seagrass reported in other distribution products or in the literature. This doesn't mean that there is like a decrease in seagrass extent. The difference is just that with satellite imagery, we are limited to shallow and not very turbid waters, and also to open areas where seagrasses can be detected. So, of course, there's going to be some limitations here. But also we can see that the proportion of the seagrass detected was very similar as shown or as found in the literature. So indicating that Florida has around 92% of the seagrasses in this whole region. Texas has 7.5% and 0.2% for Louisiana. So also we selected 15 sites for temporal seagrass mapping, and we found there was an overall increase of almost 12% in seagrass extent between 1987 and 2021, with classification accuracies higher than 80%. So only 3 out of those 15 sites showed a decrease in seagrass extent between this period, which were the Lower Laguna Madre in Texas, Charlotte Harbor in West Florida, and Biscayne Bay in South Florida. And these sites are indicated as red dots in the map. The other sites in blue are indicating positive changes in seagrass extent during this period. However, from these changes, there were only 6 that were significant. So we can see that, for example, only Biscayne Bay showed a significant decline in seagrass extent at a rate of 0.4% per year. In contrast, we observed that Clearwater Harbor showed the highest increase in rate in seagrass extent with 3.1% per year. And we didn't measure or we didn't study the causes of these changes, but these changes are usually driven by water quality in this whole region. So finally, I'd like to share the maps and results. I usually like to share these these results through these apps in Google Earth Engine. So this is an example showing the results of the seagrass changes in West Florida. This application is very easy to use and it is publicly available. Also, I will share another app showing the results of the regional seagrass mapping once the article is published. And okay, so now as conclusions, we can say that the developed mapping workflow here allowed to detect seagrasses in complex coastal waters, showing comparable results to other reference data. Uh, the satellite remote sensing for monitoring seagrass beds in the cloud, using the tools in the cloud, help us to understand how they're changing and also what makes them vulnerable. And this work provided data and results that can serve to local agencies and managers to improve conditions for seagrass recovery and conservation in the Gulf of Mexico and Florida. All right, so I will say thanks to all of these institutions, programs for the funding, data, resources that made this work possible, and also thank you all for your attention. Thanks for having me.
We're trying to clap into the mics, Luis. Thank you. Any questions in the room for Luis? Any online? I have a question then, of course. So one of the reasons we really appreciate these products is, as you know, Luis, they help fill the gaps between years for the water management district maps, which of course is our gold standard for assessing extent coverage of seagrasses in Tampa Bay. And so I know you've updated these products semi-routinely over the last couple of years. And from my perspective, it would be really awesome to kind of have these set up in a way where, each year we can get an updated estimate of seagrass cover using the methods that you've developed as sort of, again, filling those interim gaps between, the 2 years, every 2 years we get the water management district data. What would it take to produce something like that?
Yeah, that's a great question. I think that's the ultimate goal of this work, and that's something that I would like to see as well. But at this moment, that's complicated because we still need like human interaction with this. So, for example, for collecting the training and validation data, we need someone trained for doing this, and also someone like, for example, for once you do the classifications, all the stuff, we need we need to do like a post classification, which is like I showed with this with the mosaics, right? Like for example, someone supervising like that there is no if that the classification is having little noise in the image and reduce the bias like estimating and the seagrass extent. So at the moment it's like yeah we need someone dedicated for doing this, but yeah, maybe in the short future, as the technologies and tools continue to create new ways to automate for the automatization of the processes, that will be really really cool to have something like that. And of course, um, I hope to keep working on this. You know that all of these, the code and routine is available, is public. So as well, if someone else has better ideas than me and believe that my code and my workflow can be useful to develop something new or something better, yeah, go ahead. So I'm open for all of this. Yeah.
Yeah, I appreciate that. And I know that a lot of Frank Miller Carger's students have used your routines for their own separate projects. So I know it's promoting additional work. So it's definitely appreciated. And also, I definitely appreciate the apps you've put online and to those in the room and online. Uh, his presentation is linked in the agenda, so you can download that and access the links for the apps to look at the results that he's produced to date. So, any questions, other questions for Luis? Okay. Well, you're off the hook. As always, appreciate you being here talking about your work,
Thank
and
you.
I'm sure we'll be in touch in the future. Thanks, Luis.
Yeah. Thank you.
All right. Find up next we have Dr. Nazreen Alamdari. Make her co-host.
Yes, sir. So do you want me to share the presentation or?
Yes, if that works for
So
you.
my student is here, Sojib. So I think that he can share the presentation.
Would you prefer I share it?
Whatever. Yeah, maybe you can share it or he can share it. Yeah, it's no difference.
Hello,
Okay.
everyone.
Yeah, let me I will let Mohammed share his screen because it would be difficult for me to
Okay. Yeah.
I
advance
already
the
sent
slides.
the request.
Okay. You should have it now. And Luis, if you can stop sharing your screen, that would be excellent.
Yeah, okay. Let me see. I don't see how to okay.
All right. I just took control. Mohammed, I think you can share your screen now if I stop sharing. Perfect.
Uh,
Yeah, we're
Yeah,
seeing it
sounds
now.
good. Yeah.
am I audible too?
Yes.
Okay. So good morning, everyone. My name is MD Akramuzzaman Shajib, and I'm working as a graduate research assistant in Dr. Nasrin Alamdari's lab. And today I'll present our project on green infrastructure and climate change tool. It was funded by the Tampa Bay Environmental Restoration Fund, Tampa Bay Estuary program. So let's begin. Here is our presentation outline. At first, I will introduce the study area and our motivation to the work, and I'll briefly discuss about the phase 1 and phase 2, which was previously done. So the phase 1 is mainly focused on the functional model and climate data, and phase 2 is more focused on the calibration part and the climate impacts generation. In the phase 3, we will discuss more about how we uh, created a decision support tool. And finally, I'll summarize the key conclusions and recommendations. Here is our project overview. First, we aim to evaluate the effects of climate change and sea level rise on the nutrient pollution in the Sweetwater Creek watershed. And secondly, we try to identify the cost-effective green infrastructure to reduce nutrient loading. And third, we develop an interactive web-based decision support tool. We call it as Green C2SLR. I will present in details in the phase 3. So here is our study area, the Sweetwater Creek watershed. It is situated in the Hillsborough County. The watershed covers approximately 21.9 square miles and is highly urbanized with about 72% urban build-up. and there are 72 lakes and ponds. Most importantly, the watershed drains into the old Tampa Bay, which has experienced water quality problems such as harmful algal bloom, red tides, largely due to the elevated nutrient concentrations. Urbanization and population growth. Urbanization has been a major driver of water quality degradation in this region over the past 5 decades. If you see from 1970 to 2020, the area has experienced consistent population growth. This growth has increased impervious surfaces such as roads, rooftops, parking lots, which reduces the infiltration and increases the stormwater runoff. As a result, we can say the higher concentration of nitrogen and phosphorus are transported to Old Tampa Bay, contributing to the eutrophication as well as the harmful algal bloom. Here is our functional model and methodology. The process mainly begins with collecting the climate data from the 8 general circulation models with the observed station data for the precipitation and air temperature. Then these data are downscaled and bias corrected to improve their accuracy at local level. Then the corrected climate data are used to estimate the future climate conditions and to calculate the different return period rainfall intensities for the historical. We divided this as 1985 to 2014 for our observed data. Then for the near future, 2020 to 2049, and the far future, 2070 to 2099. And this data, like after calculating the rainfall intensities, we try to use this data in our swim model. This swim model is basically obtained from the Hillsborough County, and then we updated the curve number based on the land type and the soil hydro group, and then we also updated the imperviousness and the nutrient export load to get the best outcome and to match with the real world. And we calibrated our model, and then we access our swim model for the with green infrastructure and without green infrastructure scenarios to evaluate the nutrient loading for the future climate scenarios. Here is our 8 climate models we used. This climate models has a special resolutions of 100 to 500 kilometers. As this is a coarse resolutions, we had to adopt a downscaling technique, and we adopt the downscaling approach as a hybrid empirical quantile mapping with linear corrections, which mainly ensures the lower quantiles obtained with the linear corrections for the upper quantiles quantile value and preserve the mean standard deviation and higher order moments. We also published a paper based on this method for the South Florida. And then here are the downscaling approaches and the results. Here you can see the quantile plot for like empirical quantile mapping without linear correction and with linear correction. And you can see that the results indicate that the linear correction with empirical quantile mapping significantly performs higher percentiles, especially around 95th percentile, where the extreme values are critical. The improvements is evident, like we did this for the daily precipitation as well as the maximum temperature. And this improvement, you can see that there is evident more closer alignment of data points with these bisector lines. And after getting this downscale data, we followed the NOAA Atlas 14 methodology for rainfall frequency estimations. At first, we used the annual maximum precipitations values from 1985 to 2014 to be extracted and fitted to different statistical distributions such as normal, gamma, GEV, log normal. And based on the goodness of fit, we found that GEV, generalized extreme value distribution, was the best fit. And using these, we calculated the rainfall frequencies for all the DSM models, and we also validated the values against the NOAA Atlas 14. And the result shows a 3 to 10% difference, which is within, we can say that a acceptable range for the hydrologic application. Sorry. So here is our swim model. As I previously said, it was adopted from at first from the Hillsborough County, and you can see it is highly detailed. It has more than 1,000 subcatchments, more than 1,000 conduits, more than 2,000 weirs. There are 13 outfalls and 4 pumps. And after getting the model, we updated the curve number based on the USD and RCS, the imperviousness from the MRLC, the land use from the FDEP, and the EMC nutrient concentration from the EPA to match with the real world and do the calibration. Here is our calibration work, and the calibration mainly focused on 3 parameters. One is peak runoff, another is total nitrogen and total phosphorus, and we compared the model peaks with the observed peaks, and you can see the matrices with R square and NAC. This result shows a strong performance. This statistics indicate that the model captures both hydrologic response and nutrient dynamic reasonably well. Uh, for the future climate projections, the projections show several important trends. First, we can say that maximum temperature increase consistently across all the models, particularly under the SSP 585. And secondly, the extreme rainfall events become more frequent and intense, especially the far future projections. And finally, we also did a Mancandle trend analysis that indicates that temperature are in an increasing trend and the decreasing in precipitation trend, suggesting that increasing climate variability, we can say that increasing climate variability in this region. Projected changes in runoff and nutrient loads. These modeling results indicate significant increase in runoff and nutrient loads under future climate scenarios. For example, you can see under the SSP 245 near future, runoff may increase 5 to 15 million gallons, and the total nitrogen loads 100 to 150 pound. And for the SSP 585 far future, you can see it exceeds, the runoff exceeds more than 20 million gallon, and the nitrogen load exceeds more than 200 pound. So this is our phase 3, the decision support tool development. We named our tool as Green C2 SLR, cost-effective green infrastructure under climate change and sea level rise. This tool mainly integrates the green infrastructure planning, climate change scenarios, cost analysis, and the optimization algorithms. And there are 11 types of GI, for example, green roof, dry pond, wet pond, porous pavement, and more were cited here. And it also uses the NSGA2 multi-objective optimizations algorithm to balance the cost and the nutrient reduction. So here are the 6 main steps we followed to develop the tool. First of all, first one is siting. It mainly deals with the impervious data, land use, soil and elevation. And second one is the nutrient load estimations. And the third one is performance equations. It mainly deals with the nutrient reduction capacity of per green infrastructure. And then the cost equation, I'll discuss more about in the later slide. The cost equation deals with the life cycle cost analysis and the cost breakdown of each steps of GI total life frame. And the next one is applying the NSJ2 algorithm for getting the parity optimal solutions to make the best use of the optimal values. And then the user interface development, we use the ArcGIS web app builder and an Streamlit interface in renders for the cost tool. So this is the criteria table we used for the GI siting part. It is from the EPA, and it mainly deals with the drainage area, drainage slope, imperviousness, soil group, and um, the water table depth. There is also buffer zone for the road, stream, and the building. We adopted these criteria and implemented it with ArcGIS Pro to get the best location for our Sweetwater Creek watershed for getting all the GIS suitable location. So here is the cost and performance equations. Each green infrastructure type is representing using these cost and performance equations. You can see the cost equations are adopted from the IDST, International Stormwater Decision Support Tool, which is mainly made by Colorado State of Mines, and we adopted from them, and which provides the standardized lifestyle cost estimation. The cost analysis include full life cycle components, including the capital cost, operation, equipment, material, energy, maintenance, and end life cost. So total life cycle cost can be counted from using this tool. And the performance equations were adopted from the BMP train, a widely used model for estimating pollutant removal efficiencies of the stormwater control measures, and it was mainly developed by University of Central Florida. These performance equations are related to the GI area, to the drainage area, and also it compromises with the percentage of the nutrient removal. This is our NSJ2 multi-objective optimization algorithm. Here we use two minimization objectives simultaneously. One is the total cost and another is the remaining nutrient load. The result of these algorithm is a parity optimal set of solutions, which allows the decision makers to select the best trade-off between the cost and the performance. Here is our tool interface. You can see in the Sweetwater Creek watershed, there are 11 types of green infrastructures were cited based on the criteria table. And the green infrastructures are like bioretention, infiltration trench, cistern, green roof, rain barrel, wet pond, vegetative filter bed, dry pond, constructed wetland, grass soil, and porous pavement. And there are 8 available widgets to filter the climate scenario based on the SSP 245 and the 585. I'll show in my later slide. So first, the GI implementation part. Here, the GI can be cited in single or multiple. For example, in the left figure, you can see if we select only bioretention, the whole watershed will show the available locations of the bioretention. And if anyone wants to see the other GIs alongside bioretention, for example, infiltration trench or wet pond, they can also visualize using these multiple options, and it will be used by the option filtering by GI type widget. The next one is filtering climate scenario. Here we will use the filter widget, and it will allow us 3 pop-up like scenario can be chosen as SSP 245 and SSP 585, and we can also define the model. Model could be M1 to M8, the GSM models, and the period is like historical, near future, and far future. After selecting, we will just enable the green button, which will allow us to view in the next widget. It is called the chart widget. When we open the chart widget, we'll see our filtering results here, which is the initial total nitrogen and phosphorus load. Here you can see that this is for the SSP 245 and the SSP 585. And there is also an widget, we call it rainfall widget. We can also see the corresponding rainfall values, which are also a reason for these initial total nitrogen and phosphorus. So these results can be viewed from here. To getting into the cost tool after this scenario evaluation, we can just click any suitable green infrastructure. For example, I just click in this bioretention, and it will open an attribute table. And from there, the details are given, like is it the land type is private or public, then the latitude and the longitude. And if we just click on the cost tool, more info, then it will turn us into a new web page, and it is in the Streamlit interface, in the renders cloud platform, where it is open to any user. So any user can easily access this cost tool. And here the SCM, the green infrastructure, will be selected automatically. And here the user can define the available area, like how much area he wants to build the green infrastructure. And the initial total nitrogen and phosphorus concentration can be provided from our scenario filtering data from the chart data. And there is option for the required nutrient reductions. So here user can also define the how much nutrient they want to reduct. And there is also option for the confidence interval. And then if the user can place the run option, and then the result will be viewed, and the result will be in three form, like the parity optimal curve generation. And the second one is possible outcomes. It is in a tabular format. And the cost structure, the total cost breakdown. Here you can see here the results. The first one is the parity optimal optimization. It will show the total cost alongside the total nitrogen and phosphorus concentrations. And then the optimized table here, all the solutions results can be seen alongside, like all the available area corresponding to the depth, and the reduction percentage. The user can define the cost, how much money he or she want to spend here. So it is very useful for the decision makers. And then for the cost structure, it will give the total breakdown of the cost, like what is the energy cost, equipment cost, labor cost, material cost, and life cost. Everything will be given here. And there is an option for like overview cost, to compare between all the available green infrastructure. Although we selected the bioretention, we can also compare the other GI options within the same locations with the cost, whether the others are producing much cost or lower cost. We can visualize from here. So then we can show the simple calculations for the future scenarios, like if we want to keep the historical post-treatment load for the SSP 245 and SSP 585, should we increase the cost or decrease the cost? So here at first we calculated the historical load, and then we wanted to keep the historical post-treatment load for the SSP 245. And the SSP 245, it has shows that we have to do 21.24% reduction. So we at first for the historical period, we just keep it in with the margin of 15% reduction. So here for the SSP 245, we have to increase the reduction percentage. And if the reduction percentage is increased, then the cost will be increased. In the next one, we can see for the SSP 585, for the same model and the same period, it has shows that the reduction percentage could be more, like it's 25.19%, which is also more than that SSP 245. So if we want to keep the post-treatment total nitrogen and phosphorus load, we have to do the reduction higher. So here is the comparison bar chart. You can see from here for the historical period, the SSP 245 is much costly, and for SSP 585 will be more costly because of the reduction percentage increase. We also run our swim model for the with GI with the green infrastructure conditions, and compare with the without GI conditions, and from that we can summarize that GI can consistently mitigate the projected increase in runoff and the nutrient loads, and uh, however, it relative effectiveness decrease under the extreme climate scenarios, especially under SSP 585. As the cost also increases significantly if we want to maintain the same treatment performance. This highlights the importance of early implementation and the adaptive management. Here are our key conclusions that we have concluded it in the 5 regards. The first of all, climate change will intensify the runoff and the nutrient loading, and secondly, the green infrastructure can significantly reduce these impacts, and thirdly, we can say that early implementation provides the greatest benefit. And fourthly, adaptive management combining the green and the gray infrastructure could give a much better result. And finally, the decision support tool we developed, the Green C2 SLR tool, provides the stakeholders with a powerful platform for the data-driven decision making. So this is our tool QR code. You can just scan and operate our tool, and it is very compatible to any devices. So it's very easy to operate, and you can just scan and you can work with the widget. So thank you so much. Thank you for your attention. If you have any questions, I would like to answer. I think it's better to stop here, and then you can scan and play with our tool. So thank you so much.
Thank you for that. Are there any questions in the room or online? So yeah, the app is online. It's ready to go. Are there any future developments, or is it kind of in a stable state right now where it's ready to be used for planning?
Yeah, it's ready to use for planning.
Okay.
Like it's mainly has two part, the siting part and the cost tool, both is working.
Okay, great. Now, kind of a random question, and I don't know if there's a simple answer. You looked at, I think it was something like 10 different green infrastructure technologies around that mark.
11 green infrastructure.
11, okay.
Yeah.
Is there one particular technology that had sort of the highest maximum benefit in terms of nutrient removal relative to cost? Is there one that like consistently outperformed others? And I know it depends on siting and long-term performance and that sort of thing, but was there one that was like a consistent winner?
Actually, yeah, this is very uh, variable one. Like there is no consistent one because yes, depending on the cost, it is giving the optimal solutions. But if you consider the bioretention, and here you can see in the overview options, like in here you can see if we compare the overview and corresponding to the cost, you can see the wetland cost much lower, the wet pond is costing much lower, But when you're considering the available area, it requires much available area comparing to the bioretention. But when you are planning for an urbanized watershed like Sweetwater Creek, then we will focus on less area, and for the less area, bioretention and porous pavement, vegetative filter bed, these are much useful. So these GIs are depending on the situation where to use and how much money the end user wants to invest. So we can say that if this satisfies these conditions, you can implement any particular one.
And I can answer this question as well, based on what I have done in the past 10 years and in the literature. Again, it depends on the location and it depends on like what area is that, is a sidewalk, is a parking lot. But most of the time, I would say bioretention performs better than others in terms of the cost and in terms of nutrient reduction than others. And also the space that we can have the bioretention in, because wet pond probably needs more space than bioretention. But to me, to my knowledge, I would say based on the literature in different places, the bioretention.
Okay. Yeah, and I knew it wasn't a simple answer. Like you said, it depends
No, it's
on
not.
location
Yeah.
and climate scenarios. Of
Yeah. Oh,
just for
yeah.
my own knowledge, maybe others, like, is there something that's really awesome that
Yeah.
consistently outperforms the others? Um, yeah, see a question online. Randy Edwards, you have your hand raised. You want to unmute?
Yes, I understand that this is kind of a peripheral question because what this presentation is about looking at different techniques. However, I have a question in general about the climate models that you apparently you've used several and so forth. Do any of these climate models include assessment of interannual variation? By that, I mean simply, for example, if in the future year it could be very different effects on different techniques if the precipitation is varies in different ways. For example, uh, a change towards having very large events as opposed to very constant and even events could affect whether or not, and to what degree, say, a pond would have on nutrient reduction. Do any climate models, are they able to look at any interannual variation?
I can answer that question because this is not adopted in the model, I would say. But that's a good question because we have discussed with Sujib about that. And then he's going to work on in one of the objectives that he's working, because climate models are going to give us a time series of like 100 years of data. So then, yes, I have done that for my PhD as well, and he's going to do that for one of the objectives. We're going to look at these extremes and interannual variabilities and also even seasonal variabilities and see what's going on and how it's going to affect the effectiveness of green infrastructure and the cost as well. But yes, this is one of the objectives, but it's not adopted in the tool.
Thank you.
Yep.
Yeah, it's a good point, Randy, too, because you can look at the long-term trends in precipitation just from the historical data, and there is a long-term trend, but there's
Yeah.
substantial interannual variability.
Yeah.
And,
And when Soju started with me, I remember that I said,
Yeah.
so during my PhD, I had this plan to do this, but the PhD is like 3-4 years, and sometimes you cannot do all the things. So, but I had it in my mind that I want to do some work about that. So then Soju started here, and then he's going to work on that. So probably in the next couple of years, we're going to find out what's going to happen and what are going to be the solutions. So.
perfect. Any other questions?
They have a question. I can see a question in the chat. I can see, yes. SCAP. Does it apply across the entire Tampa? No, it's okay. So yes, we have developed for another project. We have a statewide tool as well. It's different from this one. That one doesn't have climate change or anything like that. It's just siting and cost optimization, but I have a statewide tool. They have developed that one too. It has different names. But then we
Yeah.
have applied and just adopted for Sweetwater Creek watershed, and then we added climate change scenarios to that and to see what's going to be the cost and how much additional costs we're going to have in the future, those kind of things. But yes, we have it statewide too.
And I think that question was from Natasha.
Yes.
And I don't know if you want to unmute, but I think it was kind of hinting at the need to sort of collect a lot of different data sources across broad regions. And
Yes, we did.
yeah, and that's, something very near and dear to my heart that I try to think about a lot, the Tampa Bay region. And if there's any way that, we can help support that, either at the Estuary program or among our partners, definitely let us know.
Yep.
Okay. Well, thanks again for that informative presentation. I think we will move on to the next agenda item.
Yeah.
Okay. Thank you, everyone. I'm stopping here.
Next presenter is Dr. Steve Myers from USF, and he's going to tell us about the wave situation at MacDill Air Force Base, huh? I think so, yeah.
Can you see it online? No. I don't know why it's not showing on the podium. Oh, presenter mode. Okay. There a pointer or? Yeah. Go. Still don't see. Yeah, hold on. It's not showing online. Do. Might have to do this on from Google. I think Microsoft is giving me problems. Is it? What's get on the screen?
I'm getting updates from online that say they can see the presentation online.
Yeah, but it's not in presentation.
Yes,
Is it in presentation mode or?
Yes.
yeah.
Mm, Maya says no.
Yeah. Gotcha. What were you saying, Blake, to do?
If you can go, whatever screen this is on, if you can get it to put it to start the presentation. There you go.
Okay. I think we're good. Okay. Steve, take it away.
So good morning. I'm Steve Mars. I'm a research scientist at the USF College of Marine Science. And my co-authors today are Mauricio Arias, Megan Kramer, and Mark Luther. Also want to acknowledge Carrie at the Estuary program, who helped conceptualize and support this project to measure the ocean wave environment around MacDill Air Force Base. And let's see. And I got it dead here. What am I missing?
Yeah, I wouldn't know if this works because it's. Yeah, I think it just hit the mouse.
Seems like you might have two screens.
There, so it must be somewhere else. So you got three.
We're seeing the McDill one now. Oh, wait.
Can you see this one?
It's progressing on line, but not up there.
Sorry, Steve.
Ah, got it.
Okay, I had a couple windows open. Is that gonna work for you?
I think it'll work.
Okay.
All right, so the reason we did this project is because there's been a lot of concern for a very long time about a loss of shoreline around MacDill Air Force Base. And we see a couple of images here over several years apart showing the loss of the shoreline and the loss of protective grasses around that shoreline. So there's been ongoing efforts going back to 2003 to stabilize the region. And those efforts, there's been about 4 or 5 of them, have met with mixed results. So there's still a lot of lingering concerns, largely about the ship traffic. There's a lot of anecdotal evidence that the wakes coming in from the ships traveling on the shipping channel, which you are outlined here in yellow, will generate large wakes that impact the shoreline and cause erosion. And we know from our previous work with the Estuary program that there are hundreds of large ship transits every year. So, and there's been anecdotal evidence, people just sitting there on the shoreline observing these. And so we decided that we needed to study the wave environment, actually go out there and make measurements. So I'll talk a little bit about wakes and their properties and how we measured them. And I'll go into the methodology. I'm not going to go into the details, the mathematics and the statistical methodologies. I'll talk more about focus on the results. And then we'll look at the ship traffic that's associated with the wakes that we were able to identify, reach some conclusions and possible recommendations for the future. And the whole idea of this was to support the design of living shorelines as new ones are coming up or being installed in the area. All right, so a ship wake, any object moving across the surface of the water is going to generate a wake. And you can see whether it's a little duck or a big ship. And it's been known since the late 1800s that there's a non-dimensional number called the Froude number or Froude number, which generally governs the production of these waves. And the Froude number increases with the speed and decreases with the size of the ship. And it turns out there's actually a maximum, for most vessels, there's a maximum Froude number, which means a maximum speed, which tends to occur around 0.4. And so this is called the limiting speed or the hull speed. And it's relevant for larger vessels and slower vessels. To actually go past this hull speed, it takes a huge amount of energy, a lot of fuel. So if you're doing international shipping, it's very inefficient. So every major ship operates below hull speed. So boat wakes are the famous V pattern that occurs behind any boat. And it has a definite angle, particularly if it's in open, deep water, it has a fixed angle. And the wakes, of course, if you're standing on the shoreline, the wake will propagate in the same direction as the boat and then away from the ship line. And there are variations. So like if you have a speedboat or powerboat and you can go past that crude number, that V is going to narrow. On the other hand, if you're in very shallow water, that V is going to spread out. It can even go almost directly side to side. So here is an example of some large ship wakes coming off some large vessels in Houston Channel. And in these restricted waterways, much like we have in Tampa Bay, you have what's nonlinear effects, which greatly distorts the wakes. And it can alters their propagation, increases their amplitude. And these images here, there's actually a recreational activities where people like to surf off the wakes coming off these ships. Right. And so you can see how the wake there is breaking, right? And so it's churning. And you can see the aerial view of the wake coming off the big tanker there as it moving towards the coast, and we see it's breaking along the shoreline. There's no images like this from Tampa Bay that I've seen. It's something that we really should do if we really want to make a more definitive connection between the wakes and the ships. All right, but what we did, so Mark designed this 2 meter by 2 meter sensor array with 4 high frequency pressure sensors, which are then placed at the bottom. So the pressure, of course, is the weight of the water on top. And as the waves come by, that height changes. And so we can record the waves that way. And we also put in what's called an ADCP, which measures the currents. And the ADCP went right in the middle of that pressure gauge array. And the whole system was placed, here, 150 meters offshore. And you can see here just visually that there's some asymmetry here because the entire western region from where we're doing the measurements is blocked. Right? You're not going to get a lot of wave energy from there. And the shipping channel is here, this line here, and it comes down and progresses through here. So there's also a lot of insulation or protection by the land for waves coming in from down here, which we'll get to in a minute. So this was the result of our deployment. This is the water depths from the 4 pressure signals. Nothing's really surprising here. This is the basic tidal signal you see in Tampa Bay, plus or minus half a meter with diurnal and semi-diurnal tides. You can also see what looks like the pen, right, that was made to draw this will be thick sometimes and then thin sometimes. That's actually the wave activity picking up. And so what we're able to do using high pass filtering is take out the tides and just leave the wave signals. So this is the non-tidal signal or the residual signal from those 4 sensors. And you see it's very noisy. It's also a bit less in amplitude on average than much less than the tides. All right, so our objectives are to separate. Oh, this is a collection of both wind waves and wakes. This is not just the ship wakes. So it's everything that's out there. So first thing we have to do is try and figure out a way to distinguish the wind waves and the wakes. And then we want to look at the wake amplitudes, their behavior, and perhaps trace them back to their source. So this is the daily power spectrum of the wake signal, the wave signal. Horizontal axis is time, vertical axis is frequency. And you can see there's basically 3 bands of energy, right? The upper band, the high frequency band, we find responds to the winds. All right, so these are wind-driven waves. The lower frequency waves do not. All right, so this is how we separate out the wind-driven waves from the wakes. Okay. Now, if we want to look at the wakes in more detail, we have to kind of zoom in because the wakes are episodic. They don't last all day long. All right, so a daily average is not particularly useful. All right, so this here, we use a wavelet decomposition. So this is zoomed in. This is about a day's worth of our non-tidal signal, just one example. And below that is called the wavelet amplitude, which on the horizontal axis is again time, and the vertical axis is frequency. And we see these blobs of energy coming out from this signal here. So those blobs are the wakes. These are relatively low frequency compared to the wind-driven waves. So we're able to use this to come up with an algorithm for detecting the waves, the wakes. We can find their peak values, we can find their duration, and then we can start looking at them in bulk. So I won't go into the details of everything we did there, but except to say that we initially found 359 wakes, or about 7 wakes a day during the I think it was 54 days that this system was deployed. Okay. Now we're particularly interested in the stronger wakes, right? Because the stronger wakes create stronger currents underneath, and the stronger currents cause more sediment resuspension. So we first filtered out for wakes that had amplitudes above 5 centimeters. And there was 108 of those. And there's some really interesting properties of these. So again, the blue is the non-tidal residual signal. And the yellow is the filter that's the waveform of the wake. And there's some really surprising properties here, very different than the wake study we did up in Felipe Park, which mostly was small recreational vessels, whereas these are very large commercial vessels. So you'll see that there's this initial run up and then a run down, right, which takes about 10 to 15 minutes to occur. Right, so that's a very long wake, very long period signal, and it's large amplitude. So the people who've stood on shore watching these things say the water comes in and then it rushes out like a little tsunami, and then it comes back in again. All right, so that's over many minutes. But the entire wake signal, then you get higher frequency oscillations, right? But the entire wake signal lasted about an hour. Right, there's one wake hitting the shoreline for an hour. So we can also take the waveform, the yellow signal, out of the just the non-tidal raw signal, and we get this orange down here, which is all this high frequency noise here. That's wave breaking, just like you saw in those pictures from Houston. You're getting a lot of wave breaking associated with these ship wakes. And again, that's important because the breaking waves will stir up the sediment even more. All right, so let's look at some quick statistics. So the amplitude of the wakes ranged up to 14 centimeters, so plus or minus 14 centimeters. And the mean duration was 69 minutes, over an hour. Now, these longer ones were examples of multiple ships coming through where the wakes are overlapping and we couldn't distinguish them. But for the most part, they're about 1 to 2 hours in duration, which is really was surprising for us. But these large wakes, there's about 2 of them a day. So it's a total persistence of about 2.5 hours a day, every day. Okay, so I mentioned that we had this ADCP, which gives us the currents. So it gives us the north-south current and the east-west current. So the north-south current is in black here. The east-west current is in green. And the gray lines, those are all the wakes that were detected. Now, the ADCP is a very power demanding instrument. So this was only out for a few weeks, much less than the pressure sensors. But during that time, there was 40 wakes detected. And so the question is, can we detect high currents during the time of those wakes? Right, so what we did was we looked at the top 1% of the current speeds for the north-south and the east-west component. Well, for the north-south, which is, parallel to the coastline, we got 11% of the extreme values occurred then. That compares to the total time of wakes being about 8.5%. So it's a little bit higher. For the east-west component, though, 35% of the extreme values occurred during these wakes. So it's very clear that the wakes are inducing high currents, which represents a risk or potential erosion. Right. So to quantify that a little bit more, we calculated the bottom shear stress. So the bottom shear stress is basically the grip or the pull that the water has on the bottom as it flows. Okay. And it increases with the speed of the water. Now, go back. So with these data sets, we're able to calculate the tidal signal and then pull that out and then just look at the waves. And then we have our decomposition of the wind-driven waves and the wakes. So it turns out that the tides themselves are really not players in terms of generating significant bottom stress. For the wind-driven waves, it's considerably higher. But when we compare the average bottom stress for the wind-driven waves and the wakes generate 50% higher bottom stress on average. So now, is that enough to start resuspending sediment? Well, there's a critical bottom stress where sediment, occurs. So you can think that, if the water is flowing slowly, not much is going on, but it gets to a certain point, things start getting picked up. Well, when we looked at it with the time periods with no wakes, it was about 5% of the time was above critical. But for the wakes, it was about 10%. And 30 out of the 40 wakes that we examined achieved at some point during their signal values above critical. So the wake, again, that's further evidence that the wakes are contributing to erosion in the area. So where are these wakes coming from? So to answer that question, we worked with our friends over at Polestar, and we got the AIS data, the Automatic Identification System, for the time period of our deployment. And this is a global traffic data system that provides ship identification, their dimensions, position, speed, types, headings, things like that. So this first graph on the left here, that is the ship speeds. And you can see the channels here where most of the traffic is confined to. And then there's some smaller traffic going here in and out, slower. And this is the vessel sizes, and the large vessels are all confined to the channel, and we're getting some smaller vessels outside the channel. That makes sense because big vessels can't go outside the channel because they will ground if they do. All right, so we had over 2,000 AIS reports from each ship at different positions, representing 93 unique vessels. Okay. So let's talk a little bit about what kind of ships are out there. Well, in terms of the size, There's basically three classes. There was a small, medium, and large group, right? Going up to about 350 meters. Okay, that's a big ship. All right. What kind of vessels were they? Well, mostly cargo and tugs. And which ones are the most active? We can count the number of times they go in and out. Well, the cargoes were very active, but the tugs were the most active. Now, that makes sense because tugs are the workhorses of any port. So they're going to be zipping around the most. And then there's the passenger vessels, which were basically the cruise liners, ferries, things like that. The speeds were all relatively small, below about 15 knots. There was a few zipping around at much higher speeds. And we looked at the distribution of that fruit number that we talked about at the beginning compared to the vessel size. And all the large vessels are operating well below that critical fruit number, that maximum fruit number. Right. Which means that they're really not, it's an indication that we're looking at nonlinear effects for the generation of these large wakes. Okay. So what are these? Let's break it down a little bit more. So the cargo ships, they're basically in two groups, around 200 meters and then over 300 meters. And the tankers are all around 200 meters in length. The passenger vessels, so again, this is like ferries over here. These are the small ones below 50 meters. And then we have the big cruise liners, which are around 300 meters. And then we have our tugs, which are all relatively small, and a smattering of other small vessels. Okay, that's what I said. So now, how do we correlate the wakes that we identified with the ships? Well, we know when the wakes occur, and we know how long it takes for the wakes to propagate from the channel to the sensors. So we backtrack, we check back in time based on that time lag, right? And first thing we see is that the majority of the wakes occurred when there was only one ship in the area. Okay. And many of these ones with two were included a tug. So we would take the tug out and just look at the big ship. So when we did that, all we're doing is partitioning by time, right? We got the data naturally partitioned into two different groups. One was an outbound group along this northern leg here, and then the other was an inbound group around the southern leg, right? Which makes sense because again, since the wakes have to propagate with the movement of the ship, inbound ships are going to generate wakes coming this way, and outbound will have a strong southern component. All right. So what are the ships doing that when the ships that we've identified were again, we're not giving attribution, it's really association. Attribution is actually a little bit of a strong term here, since we're not able to track the wake from the ship to the sensor. All we can do is look at the timing. But the ones that are associated, the ship movement that we are associated with the wakes, it was mostly the cargo ships and the large passenger ships, right? And then the tankers. And there's an asymmetry between inbound and outbound with the cargo ships and tankers, with the outbound being much more strongly associated with the wakes than inbound. And we thought, well, maybe that's because they're the way that they're moving. They're unladen, so they're going to really fly out. But then when we looked at the actual velocities, they're really not that different. Okay, so it's not the behavior of the vessels that are causing the wakes. It has more to do with the geometry of the entire system. Okay, so in conclusion, right? So that, again, the high frequency waves were all wind driven, and the vessels that are operating in the channel, the wakes they're generating contain signals of several minutes. Each pulse can be several minutes, and the entire duration is over an hour on average, right? But they're all operating well below hull speed, right? Which means that the large wake amplitudes that we're seeing are due to the nonlinearities. That is the fact that the vessels are so big compared to the channels, it becomes not nonlinear. The linear theory doesn't apply. So the passenger and cargo vessels were the most productive, followed by the tanker class. Now, the wakes are present about 10% of the time, but they do introduce, and most of them introduce or produce potentially erosive currents, right? And that the average currents induced by the wakes are about 50% more erosive than the typical wind waves. Now we have some recommendations going forward. First of all, we'd like to see some visual tracking of the wakes, maybe get some aerial photos like we saw from Houston, perhaps a series of them. That way we can make a direct attribution between the ships and the wakes. We also want to capture the wave environment, the wind-driven wave environment during a big storm. So we didn't have that opportunity with this deployment. So it's a really it's a strong contention is what's more destructive to the area, a big storm or this constant sequence of these large wakes coming through. All right, we can't answer that directly right now. The wave breaking needs to be looked at a little more, right? Because that really amplifies the erosion. And one way we can do that, at least initially, is to, first of all, the visual tracking, because the sensor is 150 meters offshore, as the wakes come towards shore, they're going, and it gets shallower, they're going to steepen, and they're going to break even more than they were than we observed offshore. All right, so that's going to impact the turbidity. So we want to have some turbidity sensors out there. Right, so we can really see how much sediment is being resuspended by the wakes. And finally, since these wakes are not driven by the behavior of the ships, but mostly by the geometry of the entire system, regulation is not really an option because, there's always the temptation to say, well, let's impose a speed limit on the ships. Well, the ships are already going relatively slow. So again, yeah, adaptation, we need to find adaptation pathways for these because the shipping industry is continuing to grow. Our population in the area is continuing to grow. We're going to get more and more ships and bigger ships, anything that can fit under the skyway. That's it. Thank you.
Thank you, Steve. Questions in the room? Got to have at least one. No one's asked questions in the room yet. Otherwise, I'll ask one. There we go.
So with this new the dredging that's going on in Tampa Bay, now that's going to allow larger ships, right? So how do you see that impacting this research?
Right. So the bigger ships are going to cause more displacement of the water as they come through. So they're probably going to generate larger wakes. Right. So yeah, so we have to figure out a way to protect our shoreline. Right. So like if you notice in the shipping channel goes right by the spoil islands in Hillsborough Bay. So those areas they've heavily protected. They got a bunch of riprap, a bunch of large debris, concrete debris and stuff there protecting those shorelines. But along McDill, they're trying to do living shorelines. And so we need to figure out ways to have a stronger, more resilient system there.
Kind of alluded to my question. You talked about adaptation, not regulation, and that's kind of the idea.
Right.
So I think, one of the larger contexts for this work is the beneficial reuse of the dredge sediment at McDill to build things like living shorelines or thin layer placement, that sort of thing, encourage seagrass growth. How, with the lead of that project, whether it's McDill or I know the Water Institute has done some preliminary work, have you interacted with them in terms of sharing this information with them, and has it influenced some of their decisions around what could be placed there? Because the wakes are gonna be hammering on anything that gets put in there.
Right. So yeah, we have shared our results with McDill. And that was a few months ago. Actually, I think you may have been in on that call. I don't know. But what they're doing with it, I don't know. I think, yeah, I'm not going to speculate what they're doing with it.
Understood.
Yeah.
So you were talking about the fact that the shipping channel is very close to 2D and 3D on the east side of the channel. Have you factored in the waves that are bouncing off those shorelines and how they're also interacting with MacDill Air Force Base?
Well, the riprap is going to disperse a lot of that, right? Because it's very irregular in structure, right? So as the waves hit that, they're going to diffract and reflect in multiple directions. So they're going to lose their coherence, right, as a wake, right? So anything that's reflecting off that we expect would be small. But it's actually a really good question. The only way to really test that, again, is through aerial observation or making sure that we can or have multiple sensors out there to look for the reflection, which is what we did in Felipe Park. So you could have, say, a second sensor on the east side of the channel and look for those kind of reflections. Then we can make estimates about how it impacts McDill. But we did not see any indication. The amount of time well, I was about to say the amount of time it takes to reflect is too long, but no, I think it has more to do with the coherence will be lost on the reflection off that riprap. So we don't really expect to see it, but we can't discount it. So I think that's something else to add to the recommendation list. Yeah.
Steve, I've got a question. Have you looked at, or is it possible to figure in the effects of sea level rise, making the water deeper and then bigger waves breaking closer to shore? And then I have a second ultra serious question. Could you develop this into a surf forecast for inside Tampa Bay?
You're actually the second person to ask that question. Because they're doing it in Houston, right? Well, I don't know if you're allowed to surf anywhere near McDill. Probably not. Sorry, what the first question was?
Sea level rise.
Sea level rise. Okay. So the amount of sea level rise we're expecting over the next 2 decades or so is probably not going to have a significant impact. All right. So, I mean, it will perhaps allow some even larger ships to come through, and you'll get larger displacement. We were talking to one of the port managers a while back, and that's what he said. He says, I love sea level rise because I can bring in bigger ships and make more money. Right. So, yes, there is the potential for increased wake activity or wake energy with sea level rise.
Want to talk? Okay. I have just a logistics question. Did you find that the reliability of this data was sufficient because you only had the one sensor, or do you wish that you had other sensors to kind of reaffirm what your findings?
Right. So the pressure sensors and ADCP data are very well developed technologies. And we placed it, we had to be careful because we had placed it out in a location where it never went dry. Okay, so the pressure sensors were always able to be active. Although for the ADCP, ADCP needs a certain amount of water to function. So when it gets a little bit too shallow, they will kind of turn off. So that's the only reliability issue that we encountered.
Okay. Thank you, Steve.
Quick break. Feel free to go right ahead. You have Jeffrey online. Oh.
Steve, you can't leave yet. I think there's an online question. I think Jesse, you have your hand raised online.
Hi, Steve. My name is Jesse Bone. I'm with NOAA HCD. Sorry if you were walking away. I couldn't see you there. I just had one more question, I couldn't tell if what was asked earlier. But I know that Nature-Based Solution has a project going off the other tip of McDill, but what you're doing does it have any alignment with what they're doing with the McDill enrichment project? Because I know they have several proposed ideas, and I didn't know if your work has any alignment with any of their proposed ideas.
This is on, yeah. So we haven't talked to them, or they haven't approached us, but like I said, we have talked to McDill about this, so they are aware. Now on the west side, there's Old Port Tampa Bay, and the ships there come in and they make a hard right turn into the port. So the wake environment is very different. We're not getting you don't have these long runways in that area like we do on the east side. The question, what I would like to see is for people to not just kind of try different living shorelines, but and maybe they're doing this now, but to use the information that we have and work with civil engineers who can actually look at the amount of stress that the living shoreline can withstand, right? Because like I said, we've seen that the wakes really do generate a lot of bottom stress, but we also need to compare that to the storms as well.
That makes sense. Yeah, I was just curious because some of the proposals that they had sent out kind of extend out past the tip of MacDill Air Force Base, and I was just wondering if some of the secondary effects would possibly maybe the currents would throw off some of the effects of what you're seeing on the east side, but I didn't know. So yeah, I can talk to them about that and maybe see if they can align with you on that on the backside.
Yeah.
But, okay. Thank you. I appreciate your time, Stephen. Thank you.
You bet. Feel free to contact us.
Absolutely. Thank you.
All right, our next speaker is Dr. Marcus Beck, all the way from the Tampa Bay Estuary program, and he'll be talking to us about what we do every day, managing the unmanageable.
Thanks. So one of the advantages of facilitating the TAC is I can put myself on the agenda whenever I want. But I try not to abuse that power. Nonetheless, I do periodically come to y'all every once in a while with what I hope aren't ideas that aren't too terrible. And my goal of this presentation is to talk about some of those ideas. I want to get feedback from you all. We have the last year or so really tried to make the TAC more engaging. And this is both informational, but my objective is to just use you all as a sounding board on some of the ideas in this talk. So that's what I'm hoping to do today. And I'll start with what is probably, hopefully, a very well-known graphic or set of graphics at this point. Really, this kind of just conceptualizes the entire management paradigm for water quality and seagrasses in Tampa Bay. It's been, as you know, largely successful over the last 30 years or 40 years to restore seagrasses, primarily through the control of external nutrients into the bay to reduce phytoplankton growth to create a light environment that will support seagrass growth. And you could see basically the long-term reduction in external nutrient loads and the long-term recovery in seagrasses. This dip right here was something that was a concern, still is a concern, even though I think maybe we've bottomed out or maybe are starting to see a slight recovery, possibly due to the drier conditions we've had the last couple of years. But this decrease from our peak in 2016 was something where we took pause and was wondering what was really going on there. And this kind of prompted this study that we published 2 years ago, looking at basically the effects of large-scale climate change stressors on the bay and seagrasses. And this is one graphic from that paper, basically showing kind of a typical story of climate change with depressing graphics of temperature going up with no end in sight. But what was also interesting was kind of we saw a trend, not nearly as strong as temperature, but we looked at salinity, and we did see a long-term, albeit a lot of interannual variability, but a long-term decline in salinity for all of the major bay segments. So really, the title of this paper was "Hot and Fresh: Evidence of Climate Change Stressors," blah blah blah. But it's getting hotter, it's getting fresher. That was sort of the take-home message there. And I wanted to follow up on this work to look at some specific questions of, well, we kind of know this is probably impacting seagrasses at some level, but there's also a regulatory context to this too. How are these things going to be influencing our ability to meet regulatory standards for water quality in the bay long term? And this is a hypothetical graphic that I often show when I talk about the likelihood of attaining water quality goals or regulatory standards. This is actually kind of made up data, but it's proving the point that under normal conditions or conditions within which a standard was developed, if those conditions were to persist into the future, there's, say, a relatively high level of certainty that if you maintain, in this case, nutrient loads at a certain threshold, you're going to attain a water quality goal. Now, you impose some external factor on there, like in this case, this is a climate change stressor. That's going to confound, your management paradigm or possibly reduce the ability or the likelihood in the future of attaining that same water quality goal at the given level that was developed possibly years ago, where you had some level of certainty that you would attain that, but you impose stress on there, and there's a much lower likelihood. So that's kind of the framework I'm thinking about when I'm looking at climate change or freshening of Tampa Bay. And I had some specific questions looking specifically at salinity. Temperature is not an aspect of this work. That might be something I'll look at in the future, but I wanted to first dive in looking at chlorophyll as one of our primary indicators of water quality, an indicator of eutrophication, something we track every year, and there's regulatory standards for that. So I wanted to see how is this large-scale, long-term freshening of Tampa Bay influencing chlorophyll. But more importantly, I wanted to dive into how salinity might be influencing that relative to loading as a primary driver, nutrient loading as a primary driver of chlorophyll, because that's the thing loading we try to mitigate or control to promote light environment or good water quality for seagrasses. Um, and so salinity would be like this elevated stressor here that's confounding the ability to meet water quality goals at the same level of nutrients. And then lastly, I was wanted to sort of project out into the future. We know kind of what the long-term trends are for salinity. How is that going to affect our ability to attain regulatory criteria, or what is the likelihood of exceeding criteria into the future if you put changing salinity on top of that? And so let me get rid of that. Can't get rid of that. Okay, so this is one of the graphics from the paper looking at chlorophyll for the major base segments, salinity showing that long-term decrease or freshening, and then loading on top of that. And so a couple things to point out here. As we all know, Old Tampa Bay is kind of the problematic bay segment here. We've been flirting above and below the threshold for a number of years. And that's kind of what this highlights here. And this graphic here shows years for each bay segment when the regulatory criteria for chlorophyll was exceeded versus when it was attained. And so you can say on the last 10 years or so, for Old Tampa Bay, we've exceeded that threshold for 5 years, basically. And this actually prompted an assessment of the assimilative capacity of Old Tampa Bay that if you've been involved with the nutrient or the nitrogen management consortium, as well as some presentations here to the TAC, we looked at this a little more carefully, a lot more carefully in terms of what is the nutrient diet or budget for Old Tampa Bay? What are we looking at to assess responses to eutrophication? Do we need to think about different ways to assess compliance, that sort of thing? So Old Tampa Bay is a big focus of this work, but I have looked at all other bay segments in terms of how salinity loading has influenced chlorophyll over the years. Loading is also an interesting one where if you look at all of the bay segments, there is, again, a lot of inter-annual variability, but it has decreased long term since the 80s, whenever, I think that's as far back as we have these estimates. Old Tampa Bay has been kind of flat in terms of the loading trend over the years, but maybe slightly increasing, which is a concern because this is where we have, chronic exceedances of chlorophyll. So we know that loading is still a factor there and possibly increasing. If you look at the stormwater loads coming in to Old Tampa Bay, those have increased quite a bit over the last 20 or 30 years. So the trends are slightly different depending on where you look, and this will flavor our understanding of when we look at the two factors, salinity and loading, how they influence chlorophyll. So 3 objectives. I wanted to use some pretty, what I think are, in the grand scheme of things, simple empirical models to look at how chlorophyll has changed over time as a function of time, but also salinity and loading. I can use those models to sort of pull out the relative influences of both of those things. And then lastly, I have some results using the models to assess the potential likelihood in the future of exceeding regulatory criteria, particularly in Old Tampa Bay, given that we know salinity is changing long term and loading will also potentially change depending on what is done or different sources that contribute to it. So the mantra of this is like, how can we account for the things we cannot control, like large scale salinity in the bay, by controlling the things we can. So if we know that salinity is going to possibly increase the likelihood, rather a freshening of the bay is going to increase the likelihood of exceeding the regulatory criteria, what do we need? What levers can we pull to account for that? So maybe we need to reduce loads even more to counteract the effects of freshening of the bay. So that's the idea, managing the unmanageable. I used EPC data, that goes back a long time, and this is actually the data we use for regulatory assessments. Going back to 1985 to 2024, looking at the water quality data, and this is the time period where we also have monthly loading data from the Nutrient or the Nitrogen Management Consortium. Basically broke it down by base segment averages for chlorophyll and base segment totals for nutrient loading by month, by year. And so I've often come up here and talked about GAMs or generalized additive models. This is, a very useful empirical modeling tool that's, a lot of analogs to just simple linear regression, but the value of these is that you can describe nonlinear trends with multiple additive functions. And these additive functions are going to be these smooth trends that can describe sort of nonlinear effects of predictors on a response variable. And so this is the basic formula here where it does look like a linear regression. You're trying to model the mean response of, in this case, chlorophyll. You have an intercept, and then you have different additive functions here denoted by these F subscripts that describe the nonlinear response of how a predictor influences chlorophyll. So this could be salinity or loading or whatever. This is the form of the model I actually ended up using. If anybody is really into GAMs, I'd love to talk to you about how this could be altered. But it's the same kind of general structure as this one. It's just showing you what I'm modeling and which predictors are put in there and how the smoothers to describe that nonlinear response are developed. So I'm modeling chlorophyll as a gamma distributed variable, which is kind of like a log normal variable, but allows variance to increase as the values increase. Pretty standard for chlorophyll. And then decimal time is going to be one of my variables I'm using to describe time. This is basically time as a number. So like July 2025 would be 2025.5. So expressing time within a year as to the right of that decimal point. Time is also described seasonally as day of year, so Julian day. Then I have salinity and nutrient load here. And then I have multiple different kind of smoothing functions here, where these ones are basically just going to be individual smoothers that just describe an individual trend of that variable, that predictor against chlorophyll. And these ones here are going to be interaction smoothers that allow the response of the predictor to a variable to change based on values of another. So this is just like any kind of conventional regression where you have fixed effects and interaction effects. It's just that we're using nonlinear smoothing functions to do this. So that's what the results look like. This is long-term chlorophyll from 85 to 2024 in the major base segments. The points are going to be the observed values, and the lines are the results I get from the model. So, it does a pretty decent job of predicting chlorophyll. We can look at it slightly differently, where this is the same thing, but instead of time being continuous on the x-axis, I have the data broken up monthly essentially and overlaid each year on top of one another to see, what is that seasonal trend, but also how there might be interannual variation between the years. And we also have up here the explained deviance of each of the models, so how well this model describes chlorophyll. Basically, it's kind of like an R squared for simple regression. So pretty good. The old Tampa Bay 74%, middle 76, Hillsborough 69, lower Tampa Bay slightly lower, but I considered this pretty much sufficient for moving forward to use these models. So that's fine. I developed the model. These are the predictions. But what I wanted to again really do, going back to my primary question, was I wanted to use these models to isolate the effects of salinity and loading on chlorophyll over time. So how do we do that? These are two variables in the model, and we can actually use the fit from the model to normalize, or in other words, remove the effects of either of these things on the predictions. And so how is that done? So there's actually an analog to this in a different type of model called a weighted regression that I think I've talked about before. But you can do the same thing with GAMs, where there's sort of two different time series I'm trying to pull out here from the predictions. There's a salinity normalized time series, and there's a salinity and load normalized time series to isolate the effects of both of those things. And so basically the approach is the same for both normalizations. With the salinity normalized approach, you have the fit model, you predict at every time step what is chlorophyll across a range of salinities, do that across the whole time series, and simply average that. The salinity and load normalized time series is the exact same thing, but you use mean loading across the time series as opposed to the observed loading. And it looks like this. So this is, I think, the model for Hillsborough Bay. These are the normalized predictions from, I don't have my time on the axis here, but this is 85 to present. Each one of these lines is going to be the predicted chlorophyll at a given value of salinity. So you can set up a matrix of predictors and set values, and you get the output. And then this is the same thing, but using mean loading. And so the normalized values are going to be the average across all of these predictions for whether it's just a range of salinity or a range of salinities at mean loading. And we really just get a time series that looks like this. So this is the points. This is an annual average of the results. So just looking at changes each year, the points are going to be the predicted values from the model at observed salinity, observed loading. But this solid line and this dashed line are going to be the salinity normalized results and the salinity normalized results at mean loading. So this red solid line is going to be the results independent of salinity, and the dashed line is going to be the results independent of salinity and loading. Okay, that's all fine and good. How do we use this information to isolate the effects of both? Well, we can look at it a little bit closer, and this is the same plot. But if we zoom in here, just as an example, I'm looking at the last 3 points here. So I think it's 2023, and 2024. These are the model predictions at the observed values that we see from the actual data. And if we take the difference between these things, so here's the predictions, here's the salinity normalized prediction. This is what I'm calling an effect of salinity on chlorophyll. And likewise, if we take the difference between the salinity normalized predictions at mean loading and the salinity normalized predictions, that's the loading effect. And this, I'm hoping this holds water in review. I haven't really seen this done anywhere, but this makes sense to me. But I can take these, they're kind of like residuals in a way, but again, they describe the individual effects of both salinity and then salinity in loading, or rather just loading here. So by taking the differences of these lines from the predictions. And so I can look at these individually. So that salinity effect here, basically the predictions minus the salinity normalized value, I can plot over time each year for each base segment to see how salinity might be influencing chlorophyll at a long time scale. So this shows those residual values, the salinity effect, each year across the 4 major base segments. And so what's kind of curious here is you see these, there's a fit to these values. I didn't look at the significance of these fits, but what I'm trying to show is that there's a gradual increase in the salinity effect over time. So chlorophyll is gradually increasing over time in each of the base segments, exception being, I guess, lower Tampa Bay here. And because we kind of know that the bay is becoming fresher long term, again, a lot of interannual variability, this increase, the salinity effect on chlorophyll over time is largely the product of freshening. And we can quantify that. It's not a large effect. It's only like, half a milligram per liter or microgram per liter or 1 microgram per liter, but it's there. And this is the same thing, but plotting it actually against salinity. So here I've taken the effects, I put it on the secondary y-axis, and I've plotted salinity flipped to kind of show you how freshening is kind of tightly correlated with this effect of salinity on chlorophyll. So this solid line here is going to be salinity flipped, so you can kind of see that there's, looks like a freshening influence, and you could see how this salinity effect follows the salinity time series for each base segment. We can do the same thing for loading. Again, that loading effect is going to be the difference between the normalized lines of salinity at mean loading or salinity normalized by itself, and look at the trend. And so again, what's kind of curious here is that although, the effects, the individual effects of loading are not particularly large, and I'll talk about that a little bit, The trends we see are kind of different by bay segment, and these do kind of follow the trends in loading that we've seen over time. So, like Hillsborough Bay, for example, there's been uh, looks like chlorophyll has decreased over time as a function of reduced loading, given that we know that largely over the last 40, 50 years, loading has decreased overall. Hillsborough Bay, or I'm sorry, Old Tampa Bay shows kind of the opposite, where we've seen an increase of loading effect on chlorophyll, and that mirrors kind of the increase in loading over time as well. So again, these things kind of follow each other. If you plot them, superimpose them on one another, just kind of the gut check of, are these signals actually following what we think they are? And it looks like for the most part they are, particularly in the upper bay segments where we have most of the loading coming in. But we can go a step further, and this is where it gets kind of wild. We can take the loading effect here and then the salinity effect here and plot them together on two separate axes. And I really don't like this plot because it's messy, but I think there are some interesting trends and conclusions you can make from this. So here's the salinity effect. So this is basically the change, again, the change in chlorophyll is a function of changing salinity, in this case, primarily freshening. And this is the loading effect. So how much chlorophyll might change as a function of how loading has changed. And so these are the four major base segments plotted by year. Each point is a year. I've connected the years. It's really hard to see, but you can kind of follow a path from one year to another. And I've color coded the points by basically cutting up the entire time period into thirds, just sort of see broadly how the effects of salinity or freshening and loading might be influencing chlorophyll long term. So I can distill this into averages for the three different slices of the long-term period and make some conclusions that I think make sense in terms of how these different factors are influencing chlorophyll long term. So if you look at this lime green color, this is the most recent time period from 2012 to 2024. Every single base segment shows a shift from the earlier time periods to the right for the salinity effect, meaning that there's an effect of changing salinity on chlorophyll in recent years. And again, I think this is a reflection of how freshening of the bay has contributed to slightly higher chlorophyll in recent years. What's also curious too is that Old Tampa Bay, not only do we see a shift to the right, but we see a shift slightly up the y-axis, indicating a slight trend towards a increased loading effect on chlorophyll as well. So both salinity and loading are showing up in this disentangled time series. Going back to this one too, you can actually see like outlier years where like 1998 pops up here extremely far on the y-axis, or sorry, x-axis. Same for Old Tampa Bay. This was a year where we had a lot of rainfall. So this shows a large salinity effect as an outlier for this year. Similarly, here's 2024. This was the year we had the three hurricanes come through. This is pretty much consistently, at least on the Old Tampa Bay and Hillsborough plots, the highest value on the y-axis, indicating that the storms contributed to a large loading effect for influencing chlorophyll. So again, kind of a gut check of like, well, what are these showing us? I can sort of take, what I know about what's happening with these years and sort of describe the trends and how they might be influencing chlorophyll. Okay, so that's all fine and good. We've kind of described this in different ways to understand how salinity and loading might be individually evaluate or affecting chlorophyll. Just some conclusions about that. Obviously, we know that the magnitude of the effects typically follow a gradient from up in the bay where we have our major freshwater inflows and freshwater influences down from middle to lower Tampa Bay. So the magnitude of the effects of both salinity and loading decreases along that gradient. All bay segments really showed a greater effect of salinity changes in recent years, as denoted by that shift in the point towards the right on the x-axis. indicating that freshening has influenced chlorophyll at some level. A lot of interannual variation. They are messy plots. These error bars overlap one another, but I think there's some kind of signal there. And both of these things are important. If you look at like loading, it looks like in the lower Tampa Bay, it's not really having a large influence, but I think that just suggests it's less of an influence in that part of the bay for chlorophyll than the other parts of the bay. So what do these actually represent? Again, loading is always going to be our primary management lever when we think about things that influence water quality. So we're not stepping away from that. I'm just again trying to disentangle the effects of either. The problem with this though is that salinity is not independent from loading in terms of the two variables, how they might be correlated, because as we know in recent years, stormwater loads are going to be have the largest influence on nutrients into the bay. So with stormwater coming in, that changes the salinity. So these two things aren't entirely separate from one another. And so it's kind of difficult to tease them apart. But what I think lower salinity, at least in this example, really describes is it's kind of a proxy for residence time. So like old Tampa Bay, you could think of like fresh conditions, lower salinity. That's when there's much longer residence time, and it creates a situation that is really optimal for phytoplankton growth. It's sitting around in the same water mass for quite some time, has much more uh, availability or time to utilize nutrients. And so that's what I think really salinity is a proxy for in this case, uh, as opposed to say just its reflection of stormwater loads. And to kind of prove that point, I've actually plotted loading here versus salinity. And yes, they are correlated. So lower salinity has higher loads, but there's a substantial amount of variation in loading that is not explained by salinity, which means I think I can sort of pull out an independent influence of salinity in these models. Okay, wrapping up here. Last thing I want to do is again, I've sort of looked at the individual effects of salinity and loading on chlorophyll, kind of looked at how that's changed over time. The last thing I want to do is, well, what does this mean long term for our ability to attain regulatory outcomes, given that we know changing salinity, freshening of the bay is going to minimize or complicate our ability to attain those thresholds at the same level of loading. So I again used the model to estimate looking at Old Tampa Bay. I actually looked at all bay segments, but Old Tampa Bay was the most interesting one because it's right near the threshold. Use the model to estimate the likelihood of attaining the standard into the future with estimated salinity reductions out to like year 50. Because I can look at, say, 1975 to present, look at the rate of change in salinity as a parts per thousand per year, and impose that 50 years out into the future of what I think salinity would be from now to year 50. So that's what it did. And I can look at different loading scenarios as well. I can fix the loading inputs in the model at observed at the TMDL, so 486 tons per year, half the TMDL, or double the TMDL, just to see how that changes the likelihood of attaining the loads. And I do this lots of times because the model has uncertainty and we got to use sort of a randomization approach to do this. So that's the salinity time series. So I looked at basically 2012 to 2024 as my representative current condition to see like how if I implicate these changes, how will it influence the likelihood of attaining the criteria. So this is what I'm starting with, the present time series. This just shows a reduction in the salinity time series based on the long-term trend. So year one is going to be, so basically present is going to be this lighter blue one. This is year 25, and this is 50 years out. So not really a large change in salinity, but it's there. These are the loading scenarios I talked about as input to the model. So blue is going to be the actual observed load for this same time series, and then scaled accordingly to whatever the situation is for half the TMDL, at the TMDL, or double the TMDL. So seeing what effect that has overall on the likelihood of attaining criteria. So I had all these setup inputs in the model. I applied it to the model and did it a bunch of times, and I get all these results that look like this. And so the way I can interpret this is these slightly transparent lines is going to be an individual run of the model with a set of inputs that I've created beforehand, whether that's salinity at present or salinity into the future or a particular loading scenario. In this case, these lines all show the results at actual loading for this time period. And these lines have uncertainty because, or there's different results in the output because the model itself has uncertainty in the parameters. So the simulation period or the simulation accounts for that when you run this a lot of times. And so this black line is the observed chlorophyll. This blue line is going to be the mean of the simulations at year 1, and then the red line is going to be the mean of the simulations at year 50. So what does chlorophyll look like 50 years in the future if conditions from 2012 to present were maintained, given that we know salinity is changing very gradually across that time period, and if we held loading at what it is presently. So we see chlorophyll increases as a function of reduced salinity. And we can quantify that from year present to year 50. What is the likelihood that we attain this regulatory threshold of 9.8 micrograms per liter right here under this constantly changing output or set of conditions we're imposing on the model? And so this is what it looks like. So this is really, I guess, present to year 50. What is the likelihood of exceeding the chlorophyll threshold under changing salinity and the different loading scenarios as different colors here? So a couple things I want to point out here. Obviously, as we change the loading, this red one is double the loading, this green one is half the loading. That proportionally increases or decreases our likelihood of attaining the regulatory standard. Makes sense. More loading, higher chlorophyll, so that passed the vibe check. Every single scenario, though, showed a very gradual increase in the likelihood of exceeding the chlorophyll threshold moving into the future. And that, again, is a function of that very gradual decreasing salinity that we're seeing in the bay. So we're at currently, this is the actual, this blue line is our actual load. This is really 40% likelihood of exceeding the criteria. Presently makes sense because you look at the last, I think 12, 13 years, 5 of those years, we actually exceeded the threshold. That's about a ratio of 40%. If we do nothing, load stays the same, 20 years, 40 years, 50 years into the future, that likelihood increases by about 15%. Fine. If we reduce our loading to half of what the TMDL is, presently we're at a 20% likelihood of exceeding that scenario or exceeding the criteria if we had half the load going in there. 50 years out, we're now at 36%. So roughly, give or take percentages where we're at presently at the observed loads. So all this is really showing you is that, we can try to maintain the current standard for the nutrients for the TMDL, but moving ahead in the future, the likelihood of maintaining water quality, of not exceeding the threshold, diminishes with more freshening of the system, assuming that continues to happen in the future, which I think is likely. And we may have to, if we are doing the same thing, hypothetically 50 years out, we may have to substantially reduce our loads to, well below 486 to counteract the effect of freshening on Old Tampa Bay. So that's it. We know the story we've been telling a long time for Old Tampa Bay is that the standards and methods used to develop the management paradigm, well, it was 30 years ago. The bay has changed quite a bit in terms of its ecology and physical conditions. And so we need to look at that original management paradigm, see if it's still valid. Yes, we think it is. Nutrients are still very important, but the ability of nutrients, holding the line might be diminished in terms of our ability to maintain a water quality environment, given the effects of freshening long term on the bay. These simple models are by that very nature simple. I know this needs to be validated with more complicated models or involved models like mechanistic modeling tools that actually describe real processes in the system. Could be something to do. And yeah, what I was saying on the previous slide, given that the bay will likely continue to decline in salinity, asking the question, is our current standard going to be sufficient in the future, given that, salinity and changes in rainfall are going to really affect the ecology of the system and really, I think, increase the likelihood that chlorophyll will only increase in the long term. So that's my harebrained idea. Would love feedback, thoughts on that. All of this stuff is available on GitHub, of course. You can look at my code and some of the figures. This is a paper I've drafted. I was waiting until I talked to you guys before I submit it, see if there's anything wild I need to change, but that's my thought. And thank you. If there's any questions, I'll take them. Randy, I think you had your hand up.
Yes, thank you. Dr. Beck, I'm going to go along with your solicitation of feedback and engagement. I have some criticisms or at least some comments, and I do not intend those to be criticism or disparagement of you or the program. I would not want to disparage you because you and I have something in common. We're fellow Gator undergraduates from the Department of Zoology, now Biology, and I just hope that these are taken as constructive. Now, to put this in perspective, the Tampa Bay Estuary program, and it was followed along by the Sarasota Bay program and Charlotte Harbor, have initially adopted the paradigm that you mentioned was really developed by in terms of loading, yielding chlorophyll, affecting seagrasses. And that was Pribble and Janicki's work over a quarter century ago. We've continued that the program, and these other programs have tended to continue that paradigm almost exclusively for this long period of time. However, it's hard to conceive of a model such as yours being accurate or useful, even though it's useful from the standpoint of food for thought, if it doesn't include the major factors, the major variables. And one thing that is not included in Tampa Bay's paradigm and in your model is that of benthic nutrient fluxes and regeneration. Back in 20 years ago, Paul Carlson and Laura Yarbo from FWC were commissioned to do a small study looking at nutrient fluxes in Tampa Bay. And to summarize quickly, they concluded that the fluxes of nutrients, nitrogen, of course we're concerned with, is as great or possibly even greater than the measured loading. That needs to be considered in any kind of overall view. I go back to the University of Florida when you were there, and even back when I was there, there was the Howard Odum Center for Wetlands. As you know, Odum was considered, along with his brother, as the father of ecosystem ecology, and one of their tenets was that in order to understand an ecosystem, you must understand all the major inputs and processes. And without including benthic nutrient regeneration fluxes, it's very hard to come up with a predictive model, I think.
Yeah.
So,
well, first of all, Randy, go Gators. Appreciate that. Yes, your point is very well taken. These models are by design simple. You're absolutely right in that there's definitely a lot of components that are missing from them. But if you go back to the original work of Ray and Tony and David Wade and others, I think one of the main philosophies or of their approach was keeping it simple. And you again, you rightfully acknowledge that there are drawbacks to that, but I do think there's value in using these simpler approaches and that they are more easily interpreted, especially when you think about them in a management application. You know, the paradigm is very simple. Lower nutrients, lower chlorophyll, better water clarity, more seagrasses. That is something everybody can understand. And I think when it comes to putting these things into practice, there's value. Um, that being said, there are better models out there that can account for these things. And the approach that we have tried to take for years is a weight of evidence approach using multiple lines of evidence to understand the ecology of Tampa Bay, not just old Tampa Bay. So we have mechanistic simulation style models that have, inputs from the watershed. It has the hydrodynamics in there. It has nutrient flux from the sediments. It's got water exchange with other, between the base sediments, you name it. And I'm calling this out specifically because it does include those components that you're talking about. But more importantly, of all the lines of evidence that we've used, the simple empirical models, the mechanistic models, other tools we've used have never, as far as I know, been contrary to one another. So even though these simple models are missing critical pieces, I do think there's uncertainty in them. And that uncertainty reflects the fact that we are missing some components, but they're telling us an overall story of the ecology of the bay that we understand, that makes sense, and that is confirmed by other lines of evidence. So if I had 20,000, 30,000 more dollars, I could do the same thing with some of our mechanistic models. But really, I think this is just a thought exercise that builds upon existing tools we have and continues to tell a story that I think makes sense in that context. So, um, I yeah, that's kind of the way I approach it, and I think that's how others have been thinking about it. And there's always more to do, more to include, but in my opinion, this tells a compelling story that hopefully gets a message across that what worked in the past might not work in the future.
If I can make further on my comments, yeah, I agree. And the point about the existing paradigm that's been used, it's valuable, has been valuable. It was a practical, simple approach that was used for mainly for relative to regulatory compliance, not so much for understanding the system. And I just always wanted to urge Tampa Bay Estuary Program, Sarasota Bay Estuary Program, to be as they attain compliance, they should be learning more and more about their system. And I haven't seen that. I haven't seen that occurring. But but there's an issue that is just even more important was that of eutrophication. It's not considered at all. These bays, through the process of loading, may becoming considerably more eutrophic. There's more organic, more nitrogen in the systems that are contributing to the actual ecological inputs. And I urge these programs to start to look at eutrophication. And I think in Old Tampa Bay, you likely have very serious eutrophication. Thank you.
Yep. Well, I appreciate those comments, Randy. And if you want to reach out and talk more, I'm happy to do so. I do want to move on to our last speaker, just to make sure they have enough time. Don is here. Great. Don contacted me a couple weeks ago. Student at St. Pete College has a capstone project that he wants to share with us. I don't know if there's any specific feedback he would like, but I'll let him explain that. Let's see, she could. have it downloaded here. Here we're just gonna have to do the.
Yeah, there's only 2 slots.
Should be able to view this full screen. Nope. All right. Does that work for you?
Sure. Yep.
Okay. All right. How's everybody doing today? I hope my statistics look as good as all y'all's statistics. First of all, thank you. I'd like to thank Dr. Beck and Dr. Day for allowing me to talk to you a bit about my capstone research, which is for me a requirement to give a presentation to a group about to either like a town meeting or a gathering like this of folks, so that you get the experience in presenting your content. But what I'd like to do, and if you don't do that, you don't graduate, period. It doesn't matter what your other 3.5, 4 years are. But what I really want to do is use this opportunity to get your input, because this is a great opportunity for me. How you doing? And some of you folks I've talked with already, and you've added invaluably to my capstone. So what is it? Really, what I'm looking at. Let's see here. Oh, it's a PC. I thought scientists only use Macs. Is this?
No.
Oh, it is a Mac. Okay, never mind. Sorry, I'm blind without my glasses. Let's see here. Can I go?
Is the scroll bar on the right?
Oh,
There
is
it
it?
goes.
Oh, this way? Oh, this way. I tried the arrow, but it didn't want to. Oh, just go up and down. Okay, there we go.
Then I think we cut you off a little bit here.
That's all right.
Oh, 2-dimensional. I'm trying to do it from on
Go
top, yeah.
Okay. Okay, so for me, I actually started this about 2.5 years ago in a research class where we had to do a lit review, which was I detested that assignment, but boy, it sure did come in handy when I started the work on this capstone. So the issue I'm really looking at is there's I originally had thought that I would do something. I wanted to do a capstone that would have an impact, and I thought, well, I'll work on a capstone that puts together a restoration of an oyster reef, and that puts in measurements and looks at how well does it work in that particular area. The whole issue of bathymetry and salt content, whatever, in order for the oysters to survive and to recruit um, um, new oysters. But then I found out there's a ton of projects going on, pilot projects, demonstration projects around. But then when you compare the number of those projects to what used to be in Tampa Bay, it's a drop in a bucket. I mean, it's something. But so why aren't we? Why, if we know, and in this, the research of my capstone is showing that we know that people believe in the benefits, the technical component of it, the fact that oyster reefs, the suitability index that you guys put out, oyster reefs are what is it, the high probability of survival in those particular areas. So the key findings then led me or instead of doing something like that, I was thinking, well, why just replicate what's already being done? So then I thought, well, we'll look at what is the reason that those projects aren't scaling. Is it because maybe the technical
component part that scientists are looking at really isn't as good as it could be to scale, or that there's a policy issue there. And so I decided I would take a look at this from the institutional perspective. What is it that's slowing, or maybe that's not allowing the oyster reefs to propagate more quickly around the bay? And that could address some of the issues. I know that the discussion about wave action and stuff that we had talked about earlier is something that, you know, I was going to ask that if I could have asked the question, I would have said, would oyster reefs mitigate some of this sediment loss from the wake? And if so, why wouldn't that be something that we would jump on? Of course, I could be way off base because I'm just jumping into this world, doing my capstone and learning a whole lot in a very short period of time. All right. Let's see here. So again, the issue is, as I said, why can't we scale faster? We've got 17,769 acres, and Tampa Bay show high restoration potential. And so we've got about 171 acres, including the demonstration projects we have going on now. We all know the current reality. We talked a lot about that already today. What I also thought was interesting is the overlap and some of the earlier presentations really hit on some of the work of C.S. Hawing when you hear the adaptive management that comes back from the 60s and 70s of how to manage, and it fits well with living shorelines, right? Because we used to think, well, we're going to go control that environment and put a hard structure out there, breakwater, that'll take care of it, and that's that. Well, that doesn't work anymore, right? And so that fed into a lot of how I was looking at what the research uncovered and how we might want to approach a solution, right? So if you, and I don't know if you've had a chance to download any of the statistics at all.
There's a lot of supplemental material from Don on the folder for the TAC that you can look at.
But I'll just summarize it quickly. Essentially, the things that, well, let me you can see basically what I did. It's mixed methods. Don't laugh at my N number, 20, because really I'm not, my intent really is to, you know, obviously I'm not concerned about generalizability really in the sense of what it is that I'm looking at, because it is unique to Pinellas County and its municipalities. But it's more designed as like a mixed methods policy analysis, right? I'm not really trying to gather, you know, a large, you know, replicable study. So, and again, I'm triangulating the survey results, which is in the presentation. So I would appreciate if you guys get an opportunity, if you haven't already, is to complete the survey. It's really quick. It's 2 minutes. Did you? Oh, thank you. Thank you. And then I did a ton of review, pretty much every document that you guys created, and plant, you know, municipality documents that had anything to do with shoreline preservation, sand renourishment, so on and so forth. And then you coded those with the 10 factors that look at the technical, the cost, the staffing, all of those things that would influence replication or growing the current demonstration projects, scaling them. And so then I did interviews. Some of you are in here I talked with. And then I coded those interviews. I have, what I'm using now, my plot device. And I went through and coded keywords that matched up with the factors. So that's where I come up with that's where the data that I have comes from. What did the data show us? Well, let's see here. I should have just put the tables in here. all around, whether it was documents, interviews, or the surveys, people believed that indeed oysteries are very feasible for living shoreline inclusion in living shorelines, the benefits of water quality, and so on. And so if we know that they work, why are we not? Why is there not more of a effort, whether it's in mostly in the policy side of things, to really move these along? Challenges that came out were permitting issues, coordination, funding, and staffing. And support exists, but formal adoption this week, we kind of already know that. I'm probably preaching to the choir for most of it. So I found three things from the data that stood out for me. In table 1 and figure 1, you can see this. They show very strong agreement that oyster reef restoration improves water quality, right? The second thing is that respondents support integrated oyster reefs into planning, but they are less certain about large-scale institutional adoption. So why is that? And the third thing, the strongest implementation barriers were funding and staff capacity, more than political risk. So with that, and again, I guess what we might want to do, and my email address is on here, because I know that you haven't had a chance to really look through the data. But I would really appreciate input in terms of, because I haven't drafted any recommendations yet, except for these things that I created for the slide, really. And my capstone talks a lot about the concept of what we were talking, adaptive management, adaptive governance, really. And that's kind of where I'm leaning in terms of my recommendations. But I really would appreciate any input that you would be willing to give me about what you think might be useful in terms of, and do you even think that this is accurate in the sense of, am I perceiving something that just is not there? Are we really rolling along and really exploiting everything we can with regard to oyster reefs? And the comparisons, I looked at a lot of different projects in New York and New Hampshire, all along the coast, in Texas. A lot of what's driving their restoration efforts are aquaculture, harvesting of oysters. And I'm not sure whether we have that here, if we have farmers in Tampa Bay at all or not, oyster farmers. But yeah, so I'm wondering if maybe that might provide some impetus tying it to aquaculture, maybe. I don't know. So with that, thank you again for sitting here and listening to this. And thank you for, if you can please do the survey and any input that you could give me based on where we're at now with the findings. Okay. Thank you.
Questions, comments for Don?
All right. I would I have a few more weeks, so I would say in the next two weeks if possible, and then I'm gonna put it to bed and hopefully that'll be that. Okay.
I think there was one comment online or a hand raised, I think from Randy.
Yes, I just have a really important suggestion, I think, to you. First of all, oyster ecology is very complex, and I am not an oyster ecologist, but I find that even the experts that I've talked to, that they said that they do not understand exactly the factors, but they're very much dependent on salinity and and dynamics of the systems. But I suggest that rather than looking at bureaucratic or governance type issues, take a look at the Apalachicola Bay program. They had a very large decline in their oysters, a complete collapse of the industry, and they've been working on it for more than a dozen years, and they've had very limited success. It's not the limitation, bureaucratic limitations. They're a well-funded program and so forth. It's a complex biological problem, and our bays and estuaries are no longer what they once were. Where oysters grew does not mean that they will grow again today. Thank you.
I appreciate that very much, and I am familiar with what you were the project in Louisiana, and I think that's a lot also aquaculture driven. But point taken. Thank you.
No, excuse me. No, Apalachicola
Oh,
Bay.
Appalachia. Sorry, I thought.
And
Okay.
it's not driven by oyster culture. It's an open bay fishery that was perhaps the largest provider of oysters in the country until it collapsed, ostensibly because of reduced inflows of fresh water from the Apalachicola River.
Okay. Great. Good point. Thank you. All right. Thank you, everybody.
Take the survey, if you haven't already.
Oh, yes. Thank you so much.
Okay, we're on the home stretch here. Thanks for hanging in there. I do have like one open discussion item, but before I do that, does anybody have anything last pressing concerns?
I have something. I wanted to just briefly go back to your presentation you provided, and it made me think of an opportunity for this entity to consider like a strategic planning approach where one might draft different management levers like you were alluding to. If one or both of those variables get exceeded at a certain point, we're saying, oh, we're seeing this trend, we should start doing this. Anyway, that's what your work made me think of, and I was excited to see it.
Thank you. Strategy is not my forte, but there are other people on our team that are very good at that. Okay. I do have, so I don't, the one discussion item I have, I admittedly don't know a whole lot about this, but this was brought to my attention. There are some materials in the folder. It's my understanding, this came up at a meeting recently, a couple months ago, actually, that there are several USGS stations, monitoring stations that are possibly or are decommissioned. There's a map of them here, relevant to our watershed. These four in particular on the Alafaya, I think monitor discharge only. So USGS is no longer, as I understand, going to be in charge of these, but the Water Management District, I think, is stepping up. So I'm just putting this in front of this group if there are any comments, concerns. I think Virginia Singer at the Water Management District would probably know a lot more about this than I do. But this was news to me. It may or may not be news to you, but I'm just bringing that up as something to think about. Ray, I don't know if we use these stations for our loading estimates. We probably do. Yeah. But I think they're going to be continuing to be out there, which is good. But yeah, reach out to Virginia Singer if you have thoughts on that. And then two announcements. First one, our annual seagrass transect training is going to be on June 18th, 9 to noon. I believe it's the same location it's always been, right on the north side of the Skyway. If you want to be a part of that, there's a registration link here. Sheila Scolaro Moffett is not going to be available this year. She's on maternity leave, so it'll be Carrie. And if I'm available, I should be there. But if you're used to going to that or have other folks that want to go, please register. And then Blake, you wanted to say something about the Bay Satisfaction Survey?
Yeah, sure. Just a reminder that our Baywide Satisfaction Survey is still open. It closes on March 31st. So this is going to be one of our initial instruments to help us gather feedback from the community and from experts in our watershed about our past and future CCMP priorities. So if you want to have your say in potential CCMP priorities that we have in the future, but also let us know about the progress we've made in the past. You've got about 2 weeks left to do it.
Yeah, and thanks to those we've bugged to fill out the survey, and thanks for doing it. Randy, you have your hand raised. Any last comments?
Yes, I have an update on the Braden River situation that I've been contacting the program about for about a year and a half, and that we discussed a little bit the last meeting.
Yes.
That's a very significant update, I would say. At that last meeting, I pointed out the reduction in observations of number of fish, including that there were very few shoreline fishes that could be observed. As the update is that since that last meeting 4 months ago, my daily observations, probably in the over 100, probably 150 observations, I have not been able to observe a single shoreline fish, such as Gambusia, Picelia, or Fungulus. They no longer exist along this shoreline, and that is a phenomenal change. I don't know any body of water in Florida that doesn't have mosquito fish in it. I did about 2 months into that. I did a survey. I looked at 3 other sites, accessible sites along the river up to a mile upstream from my observations, and I did not see a single shoreline fish. So with that, I'm not asking for or suggesting any specific action or allocation of resources of the program's funds, but I do suggest that this is an issue that is very potentially and too important to continue to just simply ignore. The Braden River is a very important nursery habitat for snook, red drum, and blue crabs. I noticed today that all the blue crab fishermen have taken their floats out, their traps out of the water. Maybe there's something being impacted there. But the fact that there are no shoreline fishes, it's also affecting the avian population. There used to be huge numbers of birds on very low tides that would be lining these islands. Now you rarely see a bird, and if it comes in a little flock of herons or egrets, and they wade down the shoreline maybe 50 or 100 yards, and they fly away because apparently there's no food for them. And I just think that we need to not wait for, we can develop an index, we can do all those kinds of things, but I just want the Tampa Bay Estuary Program to go on record that they support the fact that this is something that should be looked at. That's all I'm asking. I would ask that now. Thank you.
Well, thanks, Randy, and we hear you, and we appreciate the update on that. I think we do have some benthic special study sites that have been sampled in the Braden that should, at the very least, give us some information about what's in the sediments. And those, I believe, it's going to be a little bit till we get that information, but that might be an alternative line of evidence to consider. But thank you, Randy.
But let me say the benthic is not obviously affected. I can see tube worms burrows, and they're very numerous and so forth. So you're not going to see a dramatic effect of benthos. But fish that are totally absent, doesn't even need to be sampled. Just somebody confirm it. That's all I'm saying.
All right, heard. Thanks, Randy. Okay, well, we are pretty much out of time. Last thing I'll say is the next meeting, I had to change the date. I think it was June 3rd or something like that, but I had to push it back about 2 weeks. So just note that new date. All of our documents, our calendar reflect that. So we should be here in this room. As always, if you have thoughts on topic speakers, please let us know. And thank you all for being here and appreciate your attention. We'll see you next time. And Chair.
Meeting is adjourned.